I'm really excited to be here because it was maybe 7 years before since I last made my presentation here. It was my PhD defense. I was very excited. Now I'm very happy to show you what we did in my new university. I'm not going to stick with the same subjects that was announced to you, but this is somehow similar subjects. A holistic or integrated approach to cancer treatment technologies. Now I'm in Sakarya University of Applied Sciences, so we have a biomedical research lab there. Because it's more related to the application, we have many projects, at least 5 or 6 projects. I'm going to show you what we did. And some of my students are here. Hi. This is some view from our biomedical research lab. It was SAU before, Sakarya University. Now it is SUBÜ, the University of Applied Sciences, Uygulamalı Bilimler Üniversitesi. So we have some lab space there. So how we started this issue, I have met Professor Hun Suri from Korea. So we have met in Sakarya University in a meeting, and he showed us he was working on photodynamic therapy devices. So we invited him to our university. So this was the first step to open the lab. And then we have many application-based projects. So I'm going to show you what we do so far. These are some 5 steps, and somehow all of them are related to cancer treatment. But when I mean the cancer treatment, please, this is not a traditional methods. These 2 are related to the photodynamic therapy. These 2 are coming from TÜBİTAK projects. This is the photodynamic therapy laser system. This was a end product of a TÜBİTAK project. This is currently I'm leading this project, LED-based photodynamic therapy systems. So we did this device. And this is vein imaging system. Vein imaging used a lot of applications in cancer diagnosis or treatment or many things. And also we developed biomedical purpose micropump with PZT actuated, a simple micropump. Maybe we can use it for drug injection to the patients. And the last one is an inductive tactile sensor to find out the tumors inside the soft tissue. These 5 subjects are my applications. I'm going to start with the PDT part, okay, the photodynamic therapy. Maybe some of you knows better than me because of the photodynamic lab, photonics lab here. So what is the photodynamic therapy? Just simply, it's trying to kill cancerous tissue or cells by any form of light without damaging any healthy tissue or cell. Okay, so there needs to be 3 components. The first one is the correct light. What do I mean by saying the correct light? I will show you. And then photosensitizer injection, administration to the system, to the human or to the animal. And also there needs to be some oxygen inside the tissue. These 3 are requirements, and they somehow integrated and creates necrosis for all kinds of cells, not just for cancerous cells, but also some healthy cells. So how we can differentiate the healthy and cancerous cells? Metabolically, the healthy cells can clean themselves if you administer some photosynthesizer. Photosynthesizer means a molecule that you can activate inside by light, okay, by any forms of light. If you apply some photosynthesizer, so if there are some oxygen inside, if you apply laser or any kind of light, so you can kill the cell, which is a great approach. So what was the traditional methods to cancer treatment? First one, surgery. Second one, chemotherapy. And third one, radiotherapy. Of course, there are some other steps, but these 3 are the main ones, right? But all of them has many side effects, because you're at the same time you're damaging the healthy tissue, which is very big side effect. Whereas the photodynamic therapy has very limited side effect and easy to apply. It is cheap, and you can apply it many times. It's repeatable, maybe 10 times if you want to use it. But chemotherapy, maybe 2 times are enough. The first component was the correct light source. Why it is important? Two things. The first one is tissue penetration. If the tumor, it's not always on the surface, but sometimes it's within the tissue. So you have to reach there. But physically, as a principle, you cannot penetrate the tissue at every wavelength. You have to select the correct one. Let's say if you want to go deeply, you have to select maybe 900 nanometer. Okay. So this is one rule, is the penetration. The second one is there are some molecules which are called photosensitizers, which is activated by light. But each photosensitizer has some absorbance peak. Okay, this is ALA, aminolevulinic acid. I don't know, ALA5 or 5-ALA. We are using it in the lab also. These are the absorbance peak. So you have to target these peak by your light. So if you're using 900 nanometers, you cannot activate this photosensitizer. So you have to be very clever what you're using. The three components, remember, light, photosensitizer, and oxygen. But the oxygen side, you cannot control it. So what are those light sources that are mainly used? Lasers are most commonly used, but there are many types of lasers. This is argon lasers, metal vapor punctile lasers, solid state lasers, but all of them have some certain disadvantages or advantages. Let's say this requires high-level technical support, and this requires gold charges, which is very expensive to use it. And it has long warm-up period, and it is very huge, you see. It is really hard to make a medical device with this. And solid states are nice and compact, but very expensive. And there are also some lamps. Even with the daily light, even with the outside, you can make photodynamic therapy. But what is important then? Just check the lamps. These are their wavelength, but these are very broad wavelength, right? But these can create some heat to the tissue. You don't want to create much heat on the tissue. And these are not energy efficient. If you apply, let's say, 100 watts, you can create only 10 watts optical output. These are not very energy efficient. This one is what we are using. This is the diode laser. They are very small and easy to control, but the circuitry are quite complex. And this is example. This is 10,000 US dollar. 10,000 US dollar. So, and we corrupted one also. It's in experiment. So it's like you can buy a car, right? 10,000 US dollar. And it's enough. They have enough optical output. And what is more important, they have monochromatic, so they have very sharp wavelength. If you can target your photosensitizer with this peak wavelength, this system works perfectly. But what is the problem here? You have to control the optical output very carefully, because while you're driving this laser diode, the temperature increases. If the temperature increases, this wavelength will be shifted to the right or to the left, which means you cannot activate your photosensitizer. So there must be really good engineering, okay, the control engineering. So how we deliver to the light? We are using actually some fiber optic cables. These are some standard types. There are many types, depending on which type of operation you're doing here. There are some balloon types, there are some line types, different types. You have to carry the light. But the fiber optic cables are not efficient. You lose very much energy there. So if you apply 100 milliwatts, at the end of this tip, you have only maybe 10 milliwatts. So this is also another problem. Photosensitizer, I'm really not a chemistry guy, but somehow they developed generation by generation. Now we are at the 7th generation. There are some names. These are some companies or countries that have some FDA approval. They are using it in real human applications, human photodynamic therapy. And then the oxygen. Remember, the third one was oxygen. So why oxygen is important? What is the mechanism? When you apply a light to your photosynthesizer, it converts the O2, oxygen, to the singlet oxygen, O1. And singlet oxygen is toxic for the tissue. So if you create more singlet oxygen, this photodynamic therapy will be more efficient. So you have to understand, are you creating this singlet oxygen or not? How do you measure it? There are some chemical ways and there are some electronic ways. This is life expectancy is quite short. This is microsecond, and these are some nanosecond level. So if on the onset of the laser, this singlet oxygen starts to emit, which is I will show you. I don't remember now which nanometer, but they try to emit light. So you have to capture it. Okay, this is the evidence. But if you open the laser while you have the laser here, it is really hard to measure here. So you have to maybe make it very short. You have to close it, so singlet oxygen decays to the zero. So you have to find out this peak, right? That's why we developed, this is our first system, singlet oxygen detection system. What we use here, we use an avalanche photodiode here. Avalanche means it's like photomultiplier tube. So one photon hits the diode, so it creates maybe amplification, 1 million times amplification, so you can read the photons there. So we did some, okay, this is this singlet oxygen wavelength, so your avalanche photodiode should read between these wavelengths. Okay, so we made a probe, and then once we apply a laser to the target tissue, so we can measure now this singlet oxygen generation. So this is very nice, which means, okay, now you can cure, you can kill the cell. Everything is okay, everything is there. We just last week we just published this a new handheld singlet oxygen detection system. If you want to read, you can find on the web. Okay, this is the real guy here. Multi-mode design of a multi-mode laser system for photodynamic therapy applications. First, the designing a laser system, and then multi-mode. What is multi-mode? Why it is important? This was the first project that we write to be typed with Professor Hunsuli, and then this one accepted. I will show you the general block diagram. What are important parts? Just I want to go back. Who is the end user of this device? Who is? Medical doctors, not engineers, right? So medical doctors should use very easily. Maybe they should select the correct mode or the correct dose. Okay, you have to apply the correct photosynthesizer dose and correct light dose. Two of them are separately. This is an experimental process, but I'm not going to give very detailed. So you have to make a touch screen, which is your input module. So we used a microcomputer, which is a maybe Raspberry Pi 3, I believe. And then we use separate two ARM-based microcontroller. One of them is for cooling system. This is thermoelectric cooling by using some elements I will show you. And then the other one is for laser driver. Okay? Laser driver means you have to make a constant current supply. It should be constant because you don't want to fluctuate your output. You need some stable power output there. This is very critical part, cooling system. What do I mean? Cooling of not tissue, cooling of your laser diode. Because if your temperature gets higher, remember, the wavelength should become more shifted to the right or to the left. So this is very critical. In our case, we fix the temperature at 15 Celsius degree by Ph.D. Controller, and also we use the Ph.D. laser driver current supply. So this was our results at 500 milliwatts. This wavelength was quite sharp. 635 nanometers. Why 635? Because we are using ALA5. ALA5 have two absorbance peaks. One of them is 635, and the second reason is it penetrates the tissue more. Okay. And then this is the optical output. No, this is the wavelength stability. This is very 8 hours. You open the system. Just check the scale here. This is very nice, right? Only 0.2, 0.1 nanometer shifted. So we control it quite perfect.
There's like about an hour of stabilization. Is that?
This is not stabilization. Just check the system. This is not stabilization because it's already very close.
Very
yeah,
close.
it's already because minus plus 3 nanometers is okay.
Okay.
So this system is perfect.
Very good.
I will show
But
you.
just from the instrumentation point of view,
Yeah.
was it something that you expected? That
Yeah, the
that
fitting
shift,
time
yeah,
you mean?
about an hour or so.
Yeah, we actually we were not sure what happens, but we find our Ph.D. Parameters just by experimentally. We didn't have a model, which is quite hard, right?
Yeah.
So experimentally we find that surprisingly it was quite nice to us. And this is the long-term temperature stability. Even though it looks like very, oscillating, but check the scale here on 0.1 centigrade degrees, which is kind of perfect. And also, this is the short-term stability. After maybe 8 seconds, the system settles down by the Ph.D. So it remains stable here. And what are the modes? Why it's multi-mode? Why do we need it? There are 4 modes in our case. The first one is continuous mode. So you open the light and just wait there. The second one was the pulse mode. So you're creating just like a PWM signals. And this is the burst pulse mode, which is in these pulses you have another pulse. Okay, other pulses, which is the burst. And then this is super pulse mode. Just check the scale again. This is second, this is millisecond, this is microsecond. Let's say if you want to apply the same dose, the same amount of energy. So what do I mean? Energy is joule, right? Okay, let's make some calculations here. Light dosimetry means energy. Actually, this is a simple explanation. The underlying curve, the area of underlying curve is watt times time, right? Second. This is joule. If you want to apply the same amount of joule to the system, you have to increase the optical power output, but shorten the time. If you want to make again the same amount of energy, you have to apply high optical output. And this was the super pulse mode. Super pulse mode means applying in very relatively high energy in very short time. Why do we do this? Because of 2 things. First one is, if you apply this mode, at the same time you are heating the tissue, which is unwanted here. You don't want to heat the tissue, but you have to let the tissue to cool down. This burst signals let the tissue to cool down, okay? So the temperature will not increase. And the second one is reoxygenation. Once you apply your laser to the photosensitizer, there is some singlet oxygen generation, which means you need to wait some time to settle down the system and reoxygenate. Again, you create O1 again and again and again. So let the system reoxygenate. But it is not easy to use pulse mode, because in laser driver system, if you apply some simple systems, you will have these spikes. So you have to get rid of this by some control algorithms, let me say. So this was our optical output, I believe. Okay, this is the results, the temperature results. What is the benefit? Okay, this temperature. This is the continuous mode. These are the different joules. Just check, okay, this same amount of fluence rate. Fluence rate means joule over centimeter square. Okay. Every time the continuous mode gets the higher temperature, but the burst mode is quite stable. So this is super pulse mode. So you may prefer this mode if you apply very high energy of your application time if it is long enough. So this is very beneficial to use these modes. The other question, these systems are very expensive. We already corrected one LED, maybe two, I'm not sure. Can we use very cheap form of light, LED? I checked the literature and then I found that people are already using some LED systems maybe during last 25 years because they are cheap, they are energy efficient. If you use 100 milliwatts, you can create 98 milliwatt optical output. The efficiency is perfect. And the circuitry is easy, so it cannot create very heat because of the energy efficiency. I checked the literature. Yeah, they're using some for skin cancer, brain tumor. They do some different kind of probes. This is the LED from 1995, and this is I found different types of probes which is used phototherapy and photodynamic therapy at the same time. I found different types of system, but I couldn't find any system that is used at different modes for human experiments. These are some after surgical operation. The Emboli company produced this nice device, and speeded up the curing process here. And then I will show you an animal research. This is for colorectal cancer. I'm already doing in my lab some colorectal cancer research. So I want to check the literature. They used 3 different light sources. Maybe this is white and let me check it. Okay, blue, white, and red. Okay, so they inoculate colorectal cancer to the tissue here, and then this is the control group. This is the red light group, white light, and blue light. And blue light group, after 28 days, they removed the tumors. This is the smallest tumor here. So blue light worked perfectly. Why? Because they use alpha, which is the peak absorbance is at the blue scale. Okay, but what is the problem here? Blue light cannot penetrate very deep, so you cannot always use your blue light. So maybe you can use different light sources at the same time. Okay. I will give you some skin-related disease. So these are some examples, fully recovered examples, and it's the LED used in dermatology. And also there are different probes for rectal cancer. These probes, they show in MRI study. This is the control group. This is a sagittal and coronal views. In the control groups, tumors remains the same, while in the light group, red light group, the tumor gets 50% smaller. So it shows it can be used in maybe colorectal cancer also. Okay, just skip this. This is my TÜBİTAK project. I designed a system for experimental purposes because you have to find out which optical dose kills the tumor, right? This is a cell, what was the name of this? Bell plate, okay, thank you. You put some cell cultures inside, and you try to find out which dose kills it. So you have to make many experiments because you have to try photosensitizer dose and light dose. So you have to make many control experiments there. So I make an automatic system. So you can select the dose and then start the system. Automatically this system goes and apply the dose here. So this is the optical output. Really perfect because I use this similar laser driver module here. And also the biggest problem was here that the broad wavelength. But it's not that much important because I was targeting 635. Why? Because I want to make a comparison with the lasers. Which one is more useful? I checked the literature and the optical output level was 400 milliwatts. And my system, this system, can create 500 milliwatts, which is enough. What is the problem here? how to carry light to the patient. So fiber optic connection with LED, and it is really hard issue. So I use some temperature controller by using simple Peltier element. Peltier is a simple element. If you apply some current, one side gets hot, the other side gets so you can use this property. I fixed the temperature for 41 Celsius degree. So by controlling the temperature, you can shift this wavelength. Actually, I used 5 watts illumination purposes LED, I mean NIR LED, and then I controlled the temperature of the system. It was 625, and I shifted it 635. So which is now this is a very cheap system. The first one was 10,000 US dollar. This one is 50 Turkish lira. Okay, very cheap. And the optical output is really nice. You may expect some experimental results from me. Okay, so I'm just making our cell culture or laboratory next month, hopefully. So we are going to try it, but in the literature there are already many results. I also applied the PWM signals, I mean the pulse mode, to the LED system in order to decrease the temperature again, and it was the settling time is really fast, and I created these pulses very nicely, so it worked very well. The other question, this is a bonus example. How do you evaluate that your PDT worked? How can you understand, do you kill the cancerous cells or not? Just simply, you have to use a microscope, right? You have to check, are you living still there? Are you there? But what kind of microscope? Mostly, you have to use inverted microscope. You have to find out from here. It's kind of expensive system. I didn't have in my lab, so we started researching on lens-free microscopy. What do I mean? There are no lenses here, simply. You're only using some sensors here. You put your cell culture or your slides on top of the sensor. Okay. What is the advantage? First one, the lens-free microscopy, it is perfectly cheap. The second one is, the microscope can focus the small area, but the lens-free microscope can focus the whole area at the same time, at once, okay? It's very fast. So what is the problem here? You have to use many algorithms to get the correct image, okay? To image many back projections and things. What is the aim here? Making a system which try to understand, okay, maybe there might be some machine learning, okay? And find out these cells are cancerous, this is that, this is healthy cells. So make a comparison, maybe make some, gives your results to you. So the next step, I'm going to combine my LED systems with this microscope. Because at once you can understand which dose kills the cancer, okay? Okay, this one is one of my master students. And also we are trying to some tissue classification, because there are no colors. They are mostly, we are using monochromatic, and then you have to classify according to some data. Okay, we segmented here very correctly, I believe, because there are no ground truths here, but some doctors should check, or pathologists should check these. And also, we developed a vein imaging system. So what is the relation with the cancer? Especially for thyroid cancer, they have to make a surgery, and then on the thyroid there are some veins or nerves quite similar, and you cannot understand by eye which one is vein, which one is nerve. So it's like cutting the red cable. It's very, dangerous situation here. And some oncology patients, the veins becomes invisible. So if you want to inject it, you have to find out where it is. So we make a simple system, IR-based vein imaging system, and also use it for ID detection. What do I mean? Your pattern, vein pattern, is unique to you, just like your fingerprint. So we can use this information. Okay, we can follow you. And some obese people and dark-skinned people or infants, the vein monitoring are quite important. Actually, in the oncology department, one of the surgeons wanted to use our system in the surgery. So now we are making a project together. And this is the microcomputer-based ID detection system. First we show the vein here, and then automatically selects the region of interest. And then this was very cheap sensor that we use here. Okay, there are some pattern here. So if by using a simple thresholding, you can have your this pattern and some feature extraction. You can find out your ID if you're registered to the system. First, we register all the patients to the system, your right hand, your left hand, even your feet. We can use all the veins to register to you to the system. So what is the next question? If you can use it in the ID system, you have to make a correct encryption, because you don't want it to be stolen, right? These are information is about the people, so you have to encrypt it. So we developed a encryption method, a chaotic-based encryption method. So people only can see this image, okay? And it is really hard to solve this chaotic. We did it with chaotic model plus chaotic number generator at the same time on a microcomputer. So we encrypt it, and it works really perfectly. And so we published 2 papers. One of them is for vein imaging system. The other one is for encryption. And then maybe the 4th project. This is about the micropump, PZT, piezoelectric based actuated micropump design. So why we use micropumps in medical purpose? For drug delivery, sometimes for IV injections, sometimes there are some glaucoma diseases. So you have to inject or pump some liquid inside the eye, very slowly and controlled. So in this maybe clean room, we have modeled this and created these pumps. These are reservoirs. Let's say you put some drugs here, very in a controlled manner. You pump your drug here. We calibrated in the tactile lab, and this result. Okay, we published maybe 4 papers, and this simply, if you increase the frequency, so the displacement of the system, the actuator gets increases, and it is very linearly. If you increase the voltage, so the displacements get higher again. So, and this was really linear relation between them. And if you want to have, okay, we created 2 different micropumps, single diaphragm and bi-diaphragm. So we found that the bi-diaphragm are really perfect for high flow rate, 35 milliliter per minute, which is highly enough. We checked from the literature, so you can use. Why it is used in cancer-related research? In the chemotherapy, you're applying some drugs in a controlled manner. Okay. Okay, and this is the last project that I'm going to show you. This is my. It's very similar to my our previous project. We did it with my master students. We developed an inductive tactile sensor for lump detection in soft tissue. So how do people find the lumps in soft tissue? There are some imaging techniques, right? Let's say in breast cancer, the tumors can be found by some different mammography and ultrasound and MRI, different studies. But at first, doctors are using palpation by your fingers. So it is very objective decision. Is it really big? Is it really hard? Where it is? Is it getting bigger or smaller day by day? How can you control it? You cannot control the tumor by hand. So we make a conceptual design, and we make it like ultrasound probe. But on top of here is this silicon surface. If you apply pressure here, so you can read how much pressure you applied there. And we prepared many phantoms, and these phantoms we put some heart inclusions at different levels. Okay, and then we want to make a human versus sensor experiments, and then we developed different phantoms, and then make some experiments. First, teach the humans what kind of pressure you should apply. I will show you the results now. Okay, what is your expectation here? Humans have really nice sensors, and they made 4 different types of sensors in global skin. And but in our sample, this is not realistic maybe. If we are using, okay, let me check it. If humans are doing the same experiments, if the subjects are small and subjects inclusions are very deep, the false diagnosis rate is really high. What is the false diagnosis? If there is an inclusion, okay, this is a yes or no experiments. Did you feel it or not? Okay, the question was simple. Did you feel it or not? But 80% they were wrong. Even though there were some inclusions, they didn't feel it. But if you check the sensor output, even at small subjects, small inclusions, at deep, intermediate or surface, the sensor can create different outputs, which means it can differentiate. So it is more, might be more useful in the diagnosis of tumors in soft tissue. Of course, this is a proof of concept study. We have to develop the sensor more. These 5 or 6 subjects somehow related to the cancer technologies, but not the traditional ones. But you have to think in many aspects, I think. So these are, okay, I finished it already. These were some projects that we developed there. I'll just give you some very fast examples. So if you have some questions, you can ask me.
Can we go back to the SWOT slide?
Which one?
Single oxygen measurement.
Did you like it?
Yeah. Oh yeah, here. I have a question about that
Okay.
graph. The one on the bottom. Why are there oscillations?
These one?
Yeah.
These are noises.
Okay.
Yeah.
High level of noise.
What is the problem here? At the same time, let's say, check this. Because still the laser is on. But this is very fast. Maybe this is nanosecond, right? Nanosecond. Maybe
Yeah.
this was 100 nanosecond, even smaller. But while it is open, there are many scattering things around. And even in the room, even though we do it in a dark room, these experiments, it was really challenging. I will have another example. We will discuss it later if you want. But yes, these are noises. So we are using maybe these peak. These are not very valid to us. We just check this. Okay, if this is high enough, okay, singlet oxygen is there.
Okay.
He knows it because without singlet oxygen, PDT doesn't work.
So is there another way to prove it.
Yes,
Signal
some
formation. Yes.
chemical sensors,
Yeah, you
they
can-
use it.
Right.
The-
I mean, for this type of data, if there are objections, you can support it with some other measurement.
Yes, you're right. Exactly. What is your reference?
Right.
There is no reference here now. And also, there are some systems, the photomultiplier tubes, but hundreds
Yeah.
of millions of pounds of system. It's very,
Yeah.
expensive. We just proof of concept. It worked. We're happy. So we're going to go on, maybe compare with the other ones. Yes, you're right.
For the chaotic encryption, what do you change the seed? Like for the probably it works by chaotic oscillations, right?
Yes,
So
there
you
is a
start
model.
with the seed, and the seed is always constant, right?
You just let me check what is
maybe
the.
the collaborators.
Yes, that's why.
That's okay, no problem.
Mhm.
I just occurred to me because
Yes.
if you have like a nonlinear system and
Uh-huh.
you're working it in the chaotic regime,
Uh-huh.
so if you know the model perfectly,
Yes.
you can predict it.
Yeah.
But you start with a seed probably as an initial condition.
Yes,
right? So-
yes.
And that seed is already in the encryption system.
Yeah, actually, they don't like the chaotic encryptions just because of this. Because you have to know your
The
initial
seed.
condition, right? The seed.
Right.
Because even though you make 1 millionth, right?
And then
Yeah,
go
it,
off,
it
right.
will go off. It should be perfectly fit.
Yes.
The
Do you
initial
know
condition.
How many bits of the seed that?
Just I know it maybe one. I don't remember now, but 1 billion. We try it
Just
even
even 1
billion.
billion,
Yes.
Question about this one?
Yes.
Can you isolate the well plates from each other when you're exposing?
Yes. We are using black one. Yes. We're not using it because there are some scattering. Yes. Because this is white and opaque, and then the light affects the neighboring.
Wells.
Yes. Well. So we are using the black ones. The black ones are very perfect.
Expensive.
That's why it's white inside. This is only proof of concept.
I have a question about the opacity of the tissue. When you started the operation, the necrotic tissue is going to spread, right? About the tumor is going to start to die, and the necrotic tissue will be grow. What about the opacity of the tissue is going to change? So are you going to change your penetration range?
No.
Or still sacred?
No, you cannot do anything about the. Okay, tissue by tissue, you have to know the light tissue interaction. Okay, so it changes. The penetration then changing because the tissues are not homogeneous and different types of attenuation coefficient and things. We don't know. These are some.
The skin color, man.
Yeah. Everything affects the system. We don't know. But if it's on the surface, the system perfectly works. But otherwise, you are using some laparoscopic things. You send the cable inside and try to illuminate. Yeah, but next I really want to focus this one more because LED systems.
Can you use like there is a narrow band interference filters, like as an optical
Yes,
unit, right? So you can put those in front of the.
Yeah, but there is a
and-
problem. It reduces
Right.
the optical
But
output.
the very high, very expensive ones, the transmission
Yes,
is
you're-
pretty good,
Uh-huh.
but so of course increases the price, and instead of that you may get the laser.
Yeah, I
diode.
can buy a 50 watt LED for lightning purpose.
Right.
I can use it by using a
For
broadband.
yeah.
Yes, you're right. A narrow band, I mean.
If you use any kind of filter, make sure that the filtered light doesn't get reflected back.
Yes.
into the light.
There are anti-reflected coating we're using.
Right.
Even the singlet oxygen detection system, we used anti-scattering things, some filters. Okay.
So are you making money out of this? Not yet.
Oh, yeah. This is the pain. We are trying to
Commercialize it.
commercialize it. Yeah, okay.
Through the Technopark company? Or?
Yeah, there are some companies, but they don't have money. You need some investors, especially for photodynamic therapy part. We're planning to make a GMP space, and just planning. We don't have money.
So you would know about the details about commercialization, right? All that stuff.
Yeah. What is the problem here? The health ministry is not recognizing the PDT
As a
treatment technique. So we have to
Is it
sell it
still-
outside.
Well, it's been many years that you've been working, right?
Yeah,
Is that
China
because-
use it. Japan use it. Korea, USA, some countries, maybe 8-10 countries, they've been
About
using it
50.
25 years.
Absolutely.
Yes, and even maybe Israel.
How about some European?
Okay, do you know?
I don't know. No idea. Okay. Any questions?
Any more questions?
Çok iyi anlattın.
Thank you.